are like puzzle pieces. And you have to find the right puzzle piece to fit the right problem. So this is a note. These are our notes. So like there's no examples. And then we have a page of examples that you should have picked up. Okay? So these are notes. And then you have a page of examples and we'll do it together. So what's an identity? An identity is an equation that is true for all values for which the variables are defined. So in Algebra 1, one of your first identities that you learn is the difference of two squares. So that's the a squared minus b squared equals a plus b times a minus b. So this is an identity. And it just means that for whatever number you use or plug in, it's going to work. So for example, if the problem said 49 minus 25, we're going to choose something basic. I could break it down to be 7 minus 5 times 7 plus 5 is what this is telling me. And that's because 49 and 25 are what?
Square roots.
Perfect squares, right? And the square root of 49 is 7. The square root of 25 is 5. So 7 minus 5 gives me 2. 7 plus 5 gives me 12. So the answer would be 24. Is that true? Is 49 minus 25 equal to 24? Yeah, it is. Boom. Okay. So that's how identities work. So we're going to talk about our trig identities. But before we do that, we're going to review the unit circle. So on our unit circle, we had a circle with a radius of 1. It started at the origin, which is 0, 0. And because of that, we came up with 6 trig ratios, right? So our 6 trig ratios, what is sine?
Y over R.
Y over R, right? And if R is 1, then it's just Y. What was cosine?
X over R.
X over R. And R is 1, so it's just
X.
And tan was?
Y over X.
Boom. Remember those guys? Okay, we're going to ignore Will's response. Cosecant theta. So cosecant theta is the reciprocal of sine theta. So instead of y over r, it became, which means that since r is 1, it's 1 over y. Secant theta is the reciprocal of cosine theta, which is r over, so it became 1 over x. And cotangent theta is reciprocal of tan theta, so it becomes x over y. Hopefully, this does not look familiar. This does look familiar. Hopefully, this does look familiar. My bad, my bad. So, next thing we're going to talk about is going back to a little bit of geometry. So, with geometry, we learned the equation of a circle. So with the equation of a circle, we had x minus h squared plus y minus k squared equals r squared. And they are, h and k are your center points. Well, if we're looking at the unit circle, our h and k are 0, right? So that led us to our Pythagorean that we used, which was x squared plus y squared equals r squared. That's an ugly looking y squared there. Let me fix that. Plus y squared equals r squared. Do you remember using that to solve for different parts of the circle?
Yes, yes.
Okay, so because of these ratios and because of this equation, we have 8 identities that we can utilize to help us simplify trigonometric brain fart here, problems, situations, expressions. That's the word I was going for. I was getting there. Blame it on the 3 hours of sleep. All right, so reciprocal identities. So again, our reciprocal functions are cosecant theta, right?
Right.
Secant theta
Cotangent.
and cotangent theta. Agree or disagree?
Agree.
Agree. So when we're writing them as an identity, that means we're not using x and y. So cosecant theta is normally 1 over y, right? What does y equal? Y equals sine. So it's 1 over sine theta. Secant theta is normally 1 over x. So what is its identity?
Cosine.
1 over cosine. And cotangent theta is the reciprocal of tan. So it's actually just written as 1 over tan theta. And these are our first 3 of our basic 8s, which makes sense based on our ratios, right? We just transitioned from letters to trig values. From letters to trig values. Okay, our ratio identities are based off of tan and cotangent. So tan theta and cotangent theta are a little bit different because they're not just based off of the radius in an x or y value. They're based off what your x and y are, right? So tan theta is y over x. So in terms of a trig value, what would that be?
Sine over cosine.
Perfect. Sine theta over cosine theta.
Here's what we need part.
What? Okay. Cotangent, therefore, which is normally x over y, would be
Cosine over
cosine theta over sine theta. So do we see how these relate to our ratios? We're just taking away the x and y and writing in the trig. Okay? Just like any identity, an identity can be manipulated. So if I wanted to manipulate these by squaring them, so for example, if I wanted to have tan squared, let me fix that again. If I wanted to have tan squared, that means I would have to square the whole ratio identity. So it becomes tan squared theta equals sine squared theta over cosine squared theta. And boom, bam, I have a whole new identity. If I want it cosecant squared, then that means I would have to square its whole reciprocal identity. And now I know that cosecant squared theta equals 1 over sine squared theta. Okay? Or if I needed it to the third power, or anything, I can manipulate it. As long as what I do to one side, I do to the other, the identity is going to stay true. Does that make sense?
Yeah.
Okay? I forgot to mention about reciprocals. So when you multiply a reciprocal by its original, it equals 1. So for example, if the problem said sine theta times cosecant theta, it's going to equal 1. Because what did I do? I just multiplied both sides by sine, and what's left on its own? 1. So what would happen here?
1 would be left.
1 would still be left. If I had cosine theta times secant theta, it's going to equal 1. If I had tan theta times cotangent theta, it's going to equal 1. Because back in Algebra 1, we learned that a number times its reciprocal equals 1. So something times its reciprocal is going to be 1. Otherwise, it's not a reciprocal. Got it? Yeah, no, maybe so. All right, let's learn our next 3 identities. So our next 3 identities are called our Pythagorean identities. The Pythagorean identities are based on the fact that we know that x squared plus y squared equals
R squared.
r squared. So when you look at our first one, isn't sine squared just basically y squared? And isn't cosine squared just basically x squared? And this is my radius. So this is why this is the parent Pythagorean identity, is what I call it. So from here, I can manipulate it to form new identities. So when I'm forming those new identities, I'm just saying, what can I solve for next? What can I get by itself? So like if I wanted to get sine by itself, what would I need to move?
The square.
If I wanted to get sine squared theta by itself, what would I
The
do?
cosine.
And how do I move a positive cosine?
You subtract it.
I subtract it. So sine squared theta equals 1 minus cosine squared theta. How do we feel? If I wanted to get cosine squared theta by itself,
You would just
Minus
subtract
sine.
sine squared theta.
I would subtract sine squared theta. So that becomes 1 minus sine squared theta. What if I wanted negative versions of them? So if I wanted a negative 1 from here. In Algebra 1, we learned that if I change the sign of one side, then I have to do what?
Change the other.
Change the sign of every term on the other. So instead of a positive sign, it's going to become a negative sine squared theta. Instead of a positive cosine squared theta, it becomes a...
Negative cosine theta.
Squared theta.
Does that make sense? Well, what if I wanted negative sine squared theta? How would that affect this guy?
Make a negative.
You would have to add cosine theta.
So I would add cosine, and what happens to the 1?
This negative.
It becomes a negative. Good job. So it becomes cosine squared theta is positive, and 1 is now a negative. Remember, you're changing their signs. So if I wanted negative cosine squared theta, how would that affect this?
The sine is positive.
Perfect. Sine becomes positive, and 1 becomes negative. So it's telling you that you can solve for any term to form new identities. So this one identity created 5 new ones. It birthed them. That's why I said it's the parent. It birthed these 5 new identities. Okay? So the same thing can take place here with 1 plus tan squared. If I wanted to just have 1 equals, well, what would 1 equal?
Tan squared theta plus
Negative 10 theta.
It would be a negative tan theta. Good job. Because it's already positive, so when I move it, it becomes a negative. What if I wanted to have tan squared theta by itself?
Sin squared theta equals secant squared theta minus 1.
Perfect. Minus that 1. What if I wanted a negative secant squared theta?
the 1 and the tan become negative.
The 1 and the tan are going to both become negative because they were already positive, so they now become a negative. What if I want a negative 1?
You add positive
I'm going to end up with a positive tan and a
negative.
negative secant. And then if I wanted a negative tan, what happens here?
Negative secant, positive 1.
Perfect. I get a positive 1 and a negative secant. So that's the power of changing the signs. It doesn't make everything negative, it changes the sign. So if it's positive, it becomes negative. If it's negative, it becomes positive. Got it, sleeping beauties?
Not sleeping, but
Resting beauty, you got it?
in a way.
All right, so we're going to do the last one. See how we can manipulate that one. And then summarize our identities and do some problems. Yay! The party begins. So, 1. If I want 1 by itself,
Negative cotangent.
it's going to become a negative cotangent. Don't want to hear it. If I wanted cotangent squared theta by itself, it becomes a negative 1. Good job. Minus 1. If I wanted a negative cosecant squared theta, what happens?
They all change.
Who all changes?
The 1 and the cotangent.
The 1 and the cotangent. My C didn't make it. If I want a negative 1, What does that do?
Is it power cotangent?
Look here, Jeffrey.
Perfect. Who is Jeffrey?
Coach Brain.
I did too.
Jeffrey.
Well, look here, Leah. Focus.
I am paying attention.
Okay, and then if I wanted a negative cotangent squared,
Negative
Negative cosecant.
my one's already negative, so it's going to become a.
positive
Positive 1. And then a negative cosecant.
There we go.
Awesome.
Look at all those manipulations we just did. So proud of y'all.
Only with Tahini.
So as long as you know the parent, then all of these will just come naturally.
Where is Tahini?
No.
Okay? As long as you know the parent, then they would come natural. If you think it's hard, I kind of want you to just visualize it as this. What if the problem said 1 plus x equals y? And I said solve for 1. What would you tell me to do? Oh. So that becomes y minus x. Oh, that was so hard, right? What if I said solve for x? What would you do?
Minus 1.
Y minus
Oh, so we can isolate a variable. Okay, cool. That's all we're doing. That's it. That's all we just did. Nothing else.
It didn't seem like it.
That's exactly what we did.
Yeah, but like, it's more because you said cosecant.
Because I'm saying words with more syllables?
Yeah.
Oh, okay, cool.
If you would have just said at the beginning before we did that, all you're doing is 1 equals x.
I said you're moving. I shouldn't have to say, hey, look at this Algebra 1 pre-cal students. Mm-hmm. All right, so cosecant theta. Summarizing what we know, what we learned. So our reciprocal identities. What is cosecant theta? Try not to flip over and look. Just tell.
Cosecant, no, secant.
It's what? What's the rule?
R.
1 over sine. What is secant theta? 1 over cosine theta. What is cotangent theta? 1 over tan theta. Okay? So that's reciprocal. Next, our ratio. So with our ratio, what does tan theta equal? Sine theta over cosine theta. What does cotangent theta equal? Perfect. Cosine theta over sine theta. And last but not least, our Pythagorean identities. So our Pythagorean, that's the sine squared theta plus cosine squared theta equals 1. Then we have 1 plus tan squared theta equals secant theta, secant squared theta. And then we have 1 plus cotangent squared theta equals cosecant squared theta. Okay, so you're going to keep this paper out so that you can reference back to these identities, and we're going to do some problems.
Wait.
Ready, Betty?
No.
Well, we're going to go ahead.
Then you just destroy it.
Yep,
Why?
you just got to do it.
I mean, that's crazy.
You just do it like this.
Okay, so when we are simplifying trig functions, you want to either, we want to make this down to one trig rule or down to a number. So the main thing you want to try to think of is, can I put it in terms of sine or cosine? That's because x and y are the base of every ratio, right? So same thing for the identities. Sine and cosine are the base for our identities. So we can put it in terms of sine and cosine, we can solve the bad boy. So for example, sine is already good to go, right? So I'm not going to touch it. So sine theta is going to say sine theta. If as you're working it, you don't want to write the theta to the end, that is okay, by the way. Because I know it gets ridiculously tired of writing theta, 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 theta. But how can I change cotangent theta into terms of sine and cosine? What identity will allow me to do that? Try to cosine over sine. This is a ratio. So therefore this becomes cosine theta over sine theta. So now when I prepare to multiply, what happens?
They cancel out.
What cancels out?
The sign.
The signs. And what am I left with?
Cosine.
So my answer is just
Cosine.
cosine theta.
Oh, yeah.
See, it's a puzzle. And you're trying to figure out which piece is going to lead you to your... So this was a one-stepper.
One stepper.
I wanna go.
And that one's a 3-stepper. I'm just kidding.
We expand and then, yeah, it's 2. Okay, so here we have sine squared theta over cosine theta. They're already in terms of sine and cosine, right? I can expand sine squared because sine squared means sine theta times sine theta. Agree or disagree? All right, so we expand that one. It's no identity, just expanding. So from here to here, we just expand. That's what that says in there, scribbled. Now, how can I go from cosecant theta to either sine or cosine?
1 over sine.
1 over sine. It's a reciprocal, right? So this is going to become 1 over sine theta.
Do all the signs cancel out?
Not all,
Just one?
just 1. So 1 of sines cancel, and I'm left with sine over
Cosine.
cosine. And what does sine over cosine equal? Tangent. And that's because of a ratio. So I went from here to here because of ratio identity.
Do we have to label here?
No, we're just labeling it for notes.
Dang, that's nuts.
Labeling helps, but how do we feel?
Yeah. As long as they don't put any numbers in this
We're not there yet.
Okay.
All right, so this right here, once you see squares, you should automatically kind of think, oh, maybe I should look at my Pythagoreans. Because Pythagoreans have squared rules, right? So if I have 1 minus cosine squared x, what can that be reduced to? 1 minus cosine squared. So if I go back and I look at my rules, so I know its parent is sine squared theta plus cosine squared theta equals 1. Well, if I'm just looking for 1 minus, what does that equal? Sine squared theta. So I can reduce that down to sine squared theta. So this is now going to be cosecant squared x times sine squared x. And that's because it's a Pythagorean.
So instead of the theta, let's put x.
Yes, you can use any variable. Theta, beta, alpha, mu. I just said Greek letters for the fun of it. But yeah, you can use these later.
What?
Okay, so cosecant squared x times sine squared x. What is their relationship?
Yeah.
What is their relationship? What are they?
What?
Twins.
What is it, Faith?
Aren't they reciprocal?
There we go, Leah. They're reciprocals.
I didn't see anything else wrong.
And what do we say a reciprocal times itself? Its reciprocal is what?
1.
1. So what does this condense down to?
1.
1. So the answer is just 1. They're perfect reciprocals because they're both squared. So they're going to completely. If you don't see it that way, then think about cosecant squared x is the same thing as 1 over sine squared x. And when you multiply those, what's going to happen to your sine squareds?
They're gonna cancel out.
And what are you left with? 1. You're still using the reciprocal rule, just in a different way. All right, so now we're on 4. So on 4, I look at what I have, not much I can do. All right, let's distribute. So I distribute, and I have sine x times cosecant x minus sine squared x. Again, what are these guys? Reciprocals. So what do they equal? 1. So I have 1 minus sine squared x. I should think Pythagorean. So if I think Pythagorean, what do I get? There you go. Good job. Good job. Cosine squared. Because our variable here is a x. Terrible?
No.
Do y'all see the puzzle pieces?
Something like that.
So your identities are your puzzle pieces, and you're just like boom, boom, boom.
As long as we don't add numbers, bro.
On number 49, we like distributed.
Mhm.
So you just kept the cosecant the same.
This department's not really
Mhm. Yep. Just like if you have an x and a y, they just become xy, right?
We'll just copy somebody and forget
I would go to the
Horrible
Problem is,
people.
I would copy, but I never turn it in.
Sure. All right, so we have cotangent squared theta over 1 plus cosecant theta. There are multiple ways of approaching this, okay? The first thing I would do is always do what's the easiest thing you can see. Well, again, what is their relationship?
Reciprocal.
They're reciprocals. So I know that this becomes cotangent squared theta over 1 plus cosecant theta plus 1. We agree with that? Okay. Cotangent squared theta tells me that I should look at what? Which rules involve squares? The Pythagorean, right? And so if I go look at my Pythagoreans, and when I have cotangent squared theta by itself, what does it equal?
cosecant squared minus 1.
So if I come over here and I look, cotangent squared theta by itself equals
Cosecant squared theta minus 1.
cosecant squared theta minus 1. So I know I can substitute that in. And the reason why I'm going to substitute that in is because I already have cosecant theta there. So this tells me that it's cosecant squared theta minus 1 over 1 plus cosecant theta.
So wouldn't that cancel out?
Almost, not all of it. So y'all remember how we talked about your very first identity you kind of learned was the difference of two squares?
Mm-hmm.
Isn't this the difference of two squares?
Mm-hmm.
So the difference, the dot product here, would be cosecant
Theta times
cosecant theta minus 1 times cosecant theta plus 1. All over 1 plus cosecant theta plus 1. So what happens to my plus 1s and all that? These whole thing cancel. You. And I have a negative 1 and a positive 1. So what are they going to do? Pew, pew. And then what's left standing? Cosecant theta. Wham bam. So we went from reciprocal to Pythagorean to dot to elimination, simplifying. Okay? If this problem said x minus 1 times x plus 1, what would you tell me to do? You would tell me to do FOIL. Guess what? You should still tell me to do FOIL. Even though it doesn't say x minus 1 times x plus 1, I'm still going to do FOIL. So I have sine times sine is sine squared theta. Sine times 1 is
Sine.
just sine theta. Negative 1 times sine is
Negative sine theta.
And negative 1 times positive 1 is?
0.
Ne-
Negative 1.
negative 1. What happens to my middle?
The kids love
I have a positive sign and a
Negative sign.
negative sign. So we FOIL, we eliminate it, and we're left with sine squared theta minus 1. What should this make me think?
the
Negative
Pythagorean-
cosine squared theta.
It should make me think Pythagorean theorem.
Look at that.
And you already jumped ahead. And what does that lead me to?
Cosine squared theta.
What kind of cosine?
Negative cosine.
It's a negative cosine squared theta. Pew, 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 pew. And those are how the puzzles work. So you just have to pay attention to what you're doing. Each problem's going to run a little different. So there's no way for me to like, oh, every time you're going to get this. But they're going to run a little different. So tomorrow is going to be a whole classwork practice day of it.